Okay, today in Berkeley Seminar, we're really excited to have back our very own Evan Patterson, bringing back the program of solving equations with diagrams that there have been a couple papers on in the last couple of years, using the eGraph data structure that we've been thinking about also a lot in GATLab and now CATLab recently. Very excited to see what we got. Evan?
Thanks, Kevin. Yeah, thanks everyone for coming. So yeah, as Kevin just sort of mentioned, this talk is the intersection for me of two different lines of work. So one is this work on diagrammatic presentation of, well, originally in this case, differential equations, although this formalism doesn't really have that much specifically to do with differential equations. So this came from our work to formalize these things called Tonti diagrams that physicists, certain people working in computational physics like to draw. So this was, we wrote a couple papers on this stuff with Kevin and Tim and James Fairbanks. And then recently, I've been starting to think more about eGraphs. I don't do research on eGraphs, but I've started to just use them as a tool in my computational work. In particular, I've been using this package called egglog, which is developed by Max Wilsey's group, who's right across the street here in Berkeley. So naturally, and if you've ever seen these things, they have a very strong diagrammatic and graphical character. And if you're a category theorist, you naturally want to ask yourself, well, like, what's going on there? There must be something category theoretic going on there. And so I got to thinking about that. And it eventually occurred to me that this work we had been doing on equational reasoning with diagrams was actually really relevant to what's going on with eGraphs, or so I believe. So that's the story that I want to sort of start to tell today. I should caution that this is work in progress. So this is not a fully polished set of ideas, but I think the core of the idea is already very much there. And so hopefully it makes sense. The overall aim, I suppose, so I guess the research aim for this is to try to give a categorical and operational semantics for eGraphs. So what do I mean by that? So when you look at, if you look at some of the work on eGraphs, which goes back to 1980, the definitions that you'll see about eGraphs are typically like in terms of data structures. Like they're very concrete, which is great because it's a practical technique and you got to implement it. But the definitions tend to involve things like hash maps or like labeled graphs and stuff like that. And so the first aim is to try to give kind of a more crisp mathematical description of what's going on, and to do it using category theory. So that's the categorical semantics bit. The operational bit is to think that it's at the heart of the use of eGraphs that they're not a static thing. Like they're a data structure that you mutate over the course of a program by adding things to it and doing various operations on it. And there have been a few works over the past year or two by people in the applied category theory thinking about eGraphs, but it appears to me that they've been thinking in terms of what you might call a denotational semantics for eGraphs. So I want to emphasize the operational aspects of this, the operations that you do on diagrams to reason. So that's what we're going to talk about. Sort of just to kind of preview where we're going. So the key concepts that we'll be talking about, or at least some of these we'll be talking about, you know, is first of all the idea of a diagram in a category, which if you've done any category theory, you've certainly seen this before. Then they're sort of, I'm drawing these, I'm going to draw some arrows like in terms of like logically depends on or something. So like I'm going to talk about then something called an initial functor. This is also a classic bit of category theory, but it's not as widely known. It's not in most of the standard textbooks. So we're going to talk about what these are. These are going to be these are going to give rise to the sort of morphisms between diagrams that constitute a valid equational sort of deduction. And I'll explain that. So in this language, we're basically going to, because we'll be working with bare categories, we will, from the point of view of e-graphs, be effectively working with equational presentations where your functions are only allowed to be unary, which is fairly restrictive. So there's another thread, which is basically about how to generalize this in different directions. And the most obvious direction to generalize in is to introduce finite products. So working in a Cartesian category or also a multi-category. And that will then put you basically more into like the standard setting of e-graphs, which you can think are operating like relative to some kind of algebraic theory. And then there's sort of like how this extends to how this interacts with initial functors. So I'm not really expecting today to get to, so I think today is mainly just going to be about this. All the essential ideas are contained there. And then it's just worth noting, though, that like there is a path that I think I understand pretty well about how to upgrade this story to work in something that looks more like the standard setting for e-graphs. OK, so that's the framing. Now I want to get into the content itself. So we're going to start by reviewing some things about diagrams in a category. So just to remind you, a diagram in some category C is just a functor into that category. And the domain of that diagram is called the shape or indexing category for the diagram. What do you do with diagrams? Well, so like the things that will come to mind. So what are diagrams good for? Well, one of the things you can talk about are commutative diagrams, right? So we do this all the time in category theory and algebra. We use a diagram to express some equations between morphisms by asserting that the diagram commutes. Some other very important things, so that what the concept is usually introduced for us to then talk about limits or colimits. And I'm saying this right now because you might think that if this talk is about equational reasoning with diagrams, it's going to be about commutative diagrams. But that's not what this talk is about. So just warning up front, this is not a talk about commutative diagrams. This is really a talk about limits. And so, and why is it about limits? So the reason that limits rather than commutative diagrams will be the sort of central concept for thinking about equational reasoning using diagrams is that the intuition that one should have about limits is that a limit is an object that represents, in some sense, all possible or all the solutions to the equations encoded by a diagram, right? And so we can see this very, directly in the, the example of limits in set, right? Where if I have some diagram in set, there's a formula to compute its limit, and what that says is that I look at the tuples of elements indexed by the objects of my indexing category, and so each of these belongs to the corresponding set. But then also, these need to respect the system of equations that is described like this. We need to have that for every morphism in the indexing category, we need to have that when that corresponding function acts on xi, that should give x sub j. So this is the sense in which the limit encodes the set of all possible solutions to this system of equations. And so that's how we're going to think about the diagrams in our talk. They encode equations in this sort of style. And so then the question arises of what transformations can I do to diagrams that will preserve that will result in another diagram that presents an equivalent set of equations, which is another way of saying that the diagram has the same limit. So that's what I'm about to get into. But are there any questions so far about just like the basic framing or motivation here? Okay, so
I have one
yes.
quick, simple-minded question. What would it look like to take J and sets, or let J be? I was a little confused as to where J comes from.
So J here is just like in practice, what J comes from is it's the free category on a graph.
Oh.
Yeah.
Okay.
So
Maybe an example of the example would be nice. Like
yeah.
Parallel arrow.
Yeah.
I was going to say that.
Yeah. Right. Okay. So the right. So this is why we love category theory, because we get to have examples of examples. So the example of this example is that we take J to be, this shape, and then we can think that a diagram like this in set is a pair of parallel functions in set, and the limit of that diagram is the equalizer of f and g, which amounts to solving the equation of how do I find, well, to write it in this notation, it says how do I find x and y such that f of x equals y. Oh, so sorry. Yeah. I don't even need y, but I'm, yeah. I'll write it like like this, even though it's kind of weird, because yeah, that makes it line up with this. Okay. Okay. Yeah. Right. So an equalizer diagram is a particularly common and simple way to write down an equation using diagrams. Okay. So right. So now we want to talk. So okay. So what we want to do is give a calculus of operations that we can perform on diagrams that will preserve their limits. So the idea here is that we're going to look for, so if I have two diagrams, oops, I want to think that I start with some diagram D and in a fixed category C, and I want to turn it into some other diagram D prime with generally a different shape, by finding some kind of functor R between the shapes that make this diagram commute. And it is certainly not the case that any choice of R that you could make here would ensure that the limits, if they exist on either side, are the same. But there's a name for the special class of functors that do, and those are called the initial functors. Okay, so this will be a fun kind of definition, which is also a theorem, right? So it's going to be a definition theorem, the characterization of initial functors. So a functor from j to k is initial if any of the following equivalent statements hold. Okay, so the first one will be the definition that I just sort of wished that I had. So if for any category C and diagram indexed by K and C, there is a provided that the limits exist, so when the limits exist, there's a canonical map that goes from the limit of this diagram to the limit of the diagram I get by precomposing with R, right? Where does that come from? Well, I have these, the projection maps that go into D of Rj, but then I can pre-whisker this cone with R, and so I also get projection maps coming from here. And so then the universal property of the limit gives me a unique map into here. So if that map is an isomorphism, that's first condition. What's cool is that it is enough to consider this in the case when the category C is already set. So if the same is true just for diagrams in set, and then So the neat thing about initial functors is that they have this kind of clean conceptual definition, but you can also cache it out into something that is quite concrete. So people often say that like category theory is abstract, but what makes category theory useful, I think, is when it can be both abstract and concrete, and you can move between the two levels. So in this case, there's another way of describing this, which is to say that for every object in K, the comma category R over K, which you might call like the slice category relative to R or something, is non-empty and connected. So what connected means is that in this category, any two objects can be connected by a zigzag of morphisms. That is, there's a path between them in this category, ignoring the directions of the morphisms. Let's see. So I'm not going to prove the theorem in the talk. This is like, you can find this in textbooks. What I want to do is illustrate it mainly, well, first with some examples, and then I want to show how one can calculate using this notion. So let me give an example. It's also worth just saying that, like, I mean, we probably know what common categories are, but it's worth saying what this category looks like explicitly, just to hold it in your head, right? So the objects in this are objects in J, along with morphisms F from Rj to K, and the morphisms from, say, Jf to J prime, F prime are morphisms in the original, in the left, from J to J prime, such that this triangle commutes. Oops. Okay. So sort of the intuition here is that, okay, it might be that this functor R doesn't actually hit every object in K, but it in a sense sort of covers them, in as much as any object over here in K can be reached from the image of some object in G. So that's the non-emptiness bit. And moreover, any two choices are compatible in the sense that if I made another choice of J and F, I could connect them by some sequence of maps. So let's see. So how much time? Pretty good. Okay. So why is this called initial? Well, this example explains where the terminology comes from. So suppose J has an initial object. Let's call it 0. Then the functor that from the point to J that picks out the initial object is an initial functor. And we can give two quick proofs of this using either side of this equivalence, just to illustrate kind of how to do this stuff. So proof one is, well, we have that the limit of, whoops. For any diagram in any category, we have that the limit of the diagram, as well as the limit of the diagram pulled back along R, is the object indexed by the initial object in the indexing category. And this is basically directly from the this is like from the definition of a limit in terms of cones. This is pretty direct. But if it seems like too much a sleight of hand, we can give a sort of somehow slightly more concrete proof by just looking at what happens to this comma object. So we also then have that for any j and j, because again 0 is initial, this comma category is just is the trivial category, because there's exactly one map from R, from the image of R under this point to J by the definition of initiality, which is in particular non-empty and connected. Okay, so that's kind of a first example. So now what I want to do is get into like basically what the main thing I want to be able to make sure I get to is doing a series of calculations to show like how you can actually use this to reason about diagrams. And so now I'm going to do the first step towards that, which is to give like some patterns or motifs of initial functors that will that will give rise to what are basically rules of inference. So I'm going to give them some suggestive names. So an example of this example is that so I'm going to just fix I'm going to fix a category C, and I'm going to look at morphisms that look like this. So the picture that I drew originally over here. Oops. No, what am I doing? J prime, D prime, D, except now I'm going to have this functor R be initial. So the first sort of rule I want to introduce, we might call this operation introduction. And what it says is that if I have, let's say, this discrete diagram, then the initial functor, so this is for any morphism in C, this initial morphism of diagrams, or this morphism of diagrams is initial, which follows, actually as a special case of this example, or you can see it directly because the limit of both of these diagrams is x. So more generally, we can introduce chains of operations. So if I have for any path in C, I can say go from I can apply F1. Okay. So my next thing is I'm going to use a word that comes up a lot in the eGraph literature, which is the idea of congruence closure, which here I'll call this a congruence reduction. So if I have if I start with a span with the if I start with a span with the same map in C on either leg, then the initial functor, which sends this to just one copy of F, or the morphism of diagrams that projects both of these onto the same thing, that's initial. And again, it's just a special case of this example because these indexing categories have, or x is the limit again of both of these diagrams. And then there's one more rule that I want to be able to do. So I'll call this equation introduction, which says that suppose I know, so that say, well, suppose I have that suppose I have this commuting square. I know that this square in C commutes. Let me just, as an aside, note that in these computational applications, C will be like a finitely presented category. And so the way you would initially know some set of equations is that they would just be the path equations that are the relations in this finite presentation. So those are the equations that we might start out knowing. So if you have one of those, then suppose I'm starting from a diagram where I have, say, one side of this equation. I can introduce a parallel path with the other side in two steps. First, I can say, well, this functor this map is initial. There are a couple different ways to see that. So here I've done an intermediate step where I have one of my arrows in my indexing category actually mapping to a non-trivial composite in C. But that's just sort of an intermediate step that we need, because going in the other direction, we can then note, well, this is equal to HK, so then I can do this morphism of diagrams is also initial.
So the middle category, the middle diagram is being indexed by the non-commutative triangle.
Yeah, so okay, so yeah, thanks for asking, Kevin. All of the indexing categories for diagrams I will use are free categories. So yeah, and that matches. I mean, nothing about the formalism makes you have to do that, but that sort of matches the way that you would implement this with data structures, where like your diagrams, the indexing thing for your diagram will just be some graph. Yeah.
So is that why you need to start off with, like, in this case, a commuting square as opposed to just like a commuting parallel pair in C?
Oh yeah. So thanks for asking that as well. I could have picked any equation between paths of arbitrary lengths. I just chose the square to illustrate how if I want to do yeah, if I like, I think I see what you're saying. Like if I had just started with a parallel pair, I wouldn't have to do this intermediate step. So this is just showing that like for any path equation, regardless of how long the paths are, you might need to take an extra step, but you can do this. You can make this move. This is a valid move. Okay, and so I'll also just remark quickly that like there is with some more theoretical development, you can know that initial functors are stable under pushout, which basically shows that each of these sort of like these rules, if you apply it using the sort of like rewriting style pushout stuff, will result in initial functors. But I'm not going to go into that in detail. What I want to get into are some calculations to show how show how you can calculate. Okay, so I want to prove so I want to show how we can prove the pasting law for, say, like commutative squares. Is how people would normally say it. So like if I have, so what I'm given is as assumptions, say, oops, let's say that I have, say that I have let's say that I'm given this. So in other words, right, like what I'm really saying here is that C is the category that's finitely presented by like these objects and these morphisms subject to path equations. And so now what I'm going to do, so this is like my computation. So I'm going to say I'm going to compute. I'm going to start. So I'm going to start with the singleton diagram. Its limit trivially is x. I am going to then do some stuff. So I'm going to well, I'll just start drawing things and then say with words what I'm doing. So I want to try to prove this in some style where acting as if I didn't already know the answer, right, but just sort of like following my nose. So like if I wanted to prove that the composite square outer rectangle commutes, I can just start by saying, well, I'm going to do operation introduction on x to give myself both sides of this equation. Okay, so basically I'm applying this rule twice. Then what do I do? Well, I can recognize that, like, right, I see this path, hf prime, and that's the left side of one of my equations. So I can do equation introduction. So this is op intro. So I'm going to do equation introduction. And so then I form, so same thing upstairs. Haven't changed that. But now I have h f prime y prime. What do I have? F y and k. So I've introduced that equation. But now I can say, oh, look at this. I have now two copies of f coming out of the same object. So I can do a congruence reduction and merge these together. So I have I now have, oh, I'm sorry, I missed part of my diagram. I had one more thing. Oh, but now, where am I? Right. And now I have an opportunity to apply to apply an equation here. So I can do equation introduction to get f y. I keep losing bits of my. Sorry, I keep losing like bits of trailing data here. X, Y, Z, C prime. So then I have. So this is G prime, Z prime. I get another copy, G, Z, L. Now, in a sense, I could already stop here, but I may as well just like clean up this diagram a bit by congruence closing it again. And then I'm going to get the, so if I do that, I get the rectangle this. Okay, but so what have we done though? So the limit of this diagram was trivially x. Therefore, the limit of this diagram must also be x. And that means that any two paths starting at x with the same target have to be equal. And therefore, we've proved that the outer rectangle commutes. Yeah, so we, yeah, okay. So I'll just conclude that I'll just write this limit of final diagram is x. Therefore, outer rectangle must commute. Does that make sense? Does that calculation make sense? Yeah.
Cool that actually leads to
Yeah.
commutativity, even though you only talk about
Yes. So there's something sort of sneaky about that, which can try to say a little bit about later, if I have time. Yeah.
Sorry, where's the initial functor in this example?
Sorry. So yeah. So each time I passed from one of these to one of these, I used either one or two initial functors. When doing operation introduction and congruence reduction, I used a single initial functor going in the forward direction. And then when I did equation introduction, I used a zigzag of initials like this. So what I've done is I've created a zigzag of initial functors all over this category C that takes me starting from here to here. And as a result of the definition of being initial, that leads to this, that shows that the limit of the diagram that I started with, which was trivially x, has to still be the limit of the diagram.
So you showed an initial functor from this.
I showed a zigzag of initial functors, so they're not all pointing in the same direction. But maybe this is it, since you're saying this. This is it. Well, yeah.
Well, and since, as you mentioned, they're closed under pushouts, you could just take the, you could just close that zigzag
Yeah.
under pushouts.
Yeah.
And then get
You can. Yeah. Right. I think there's even some result that there's like a calculus of fractions or something for initial functors. But this is a good opportunity to introduce kind of the definition that's sort of implicitly behind this that Kevin and I and others have studied in a previous paper. So we'll say that well, do I still have the picture? We'll say that that this map is what we'll call a weak equivalence between the diagrams D and D prime. That is, it's a map in the slice category over C with the further property that the functor is initial. And then we'll say that building on that, we'll say that two diagrams in a common category C are weakly equivalent if they can be connected by a zigzag of weak equivalences. Huh?
You defined weak equivalence?
I defined.
Yeah.
So what I'm doing in this calculation is I am proving that this final diagram is weakly equivalent to this trivial diagram. I wanted to do another calculation, which is the let's see, I've got, let's see. So I wanted to do one more calculation, which would have been actually the running example in the original work on egraphs, which is basically a calculation in a finitely presented monoid. That's a fun calculation. The good news is I have a blog post drafted on this stuff, which I'll publish shortly, which will have that example, so you can find that. But that example would have been fun because it will make it quite clear that it's connected to the sort of calculations that people are doing with egraphs. there's more that I wanted to have said, in particular, trying to think about how to push this a bit closer to the sort of data structures that people use when they work with eGraphs, but that's work in progress anyway. So maybe now's a good time to stop and take questions. What I hope you took away from this is that there is like a mechanizable calculus of weak equivalences, and we can use it to do diagrammatic reasoning in, for example, finitely presented categories. So thanks. Yeah. Yeah.
Is there an easy way to connect this up to equational reasoning in universal algebra and logic, where you just have a set of equations and you do substitution and,
Yeah. So I think that becomes more apparent when you, so at the beginning I alluded to like a generalization of this story that would, rather than doing everything in bare categories, you're working in categories with finite products. And the notion, it's not so obvious, but it turns out that the notion of initial functor basically works without needing to change anything in that setting. But then you can see basically that the but the way we would typically work in that setting is like if you have some like Cartesian, well, let me say multi-category actually, because the way I want to have the kind of diagrams I want to look at then are maps from like the free, well, actually, oh, sorry, I'm going to start with a Cartesian category C, and then I'm going to look at diagrams that are maps from the free Cartesian category on some multigraph called G, where a multigraph here, I don't mean it in the sense that graph theorists sort of sometimes use it, but in the sense of like the generating data for a multi-category. And this syntactical construction, the free Cartesian category on a multigraph, is precisely one way to perform that construction is to construct the expression tree, like the terms that people would normally use in algebraic theories. You build this out of terms where the operators are the morphisms in this multigraph, and then in that setting you really see the syntactic. You can see the syntactic side come out. Yeah. Mm-hmm.
So, this is really cool.
Yeah.
So I have a bunch of questions.
Yeah.
Maybe I'll let other
Yeah.
people help. But so one thing I have is just like, so when I see something like this, sort of the first thing I think of is like, okay, how deterministic is this
Yeah.
sort of like rewriting process?
Yeah.
So like some initial questions are like, is this sort of like set of rules you have for initial functors complete?
Yeah.
For
That's a great question. So I don't know. That's definitely a theoretical question one would want to try to answer. Like, assuming that all your diagrams are like free and finitely generated, can you give like a minimal but complete set of rules that would generate any initial functor? It's a great question. I don't know. Yeah.
The normal way to give a kind of complete generated set quote unquote is in the factorization system sense.
Yeah.
It's easy to give initial functors such that everyone is like positive coproducts and pushouts of it, but that's not really what you want here as far as actual zigzag completeness.
Yeah. I will say though that I actually, right, so that's definitely a good question that you would want to ask. I also think though it's sort of it's a little bit of a virtue of this approach that, right, like initial functors compose, and moreover, as you pointed out, like even these zigzags can be reduced. And so like it gives you, as an operational semantics, if you will, it's quite flexible in that it doesn't insist that you perform things one minimal step at a time, which is actually very relevant in practice. Like when part of what made this eGraph technology become practical is people finding clever ways to imply in batch a whole bunch of changes. And that just, I think that ought to just correspond to just building up a more complicated initial functor as opposed to insisting that it come from one of these generating rules, if you will. Yeah.
Yeah. When I've encoded rewrite eGraphs as like a specific type of like C-set
Yeah.
and compute the quality saturation with rewriting,
Yeah.
the things that you would, the rules are precisely the three things that you've got right there.
Nice.
All those initial functions are precisely
Nice.
the things that I would sort of like
Nice.
maybe in an ad hoc way
Yeah.
just read off of
Yeah.
so it's and the fact that you can compose rules together and to make
Yeah.
composite rules might exactly correspond.
Yeah, no, I really do think that people are doing stuff like this. I think that the novelty of the talk, if there is any, is in recognizing that it's connected to this concept of initial functors. Yeah. Yeah. Yeah.
I might have missed this, or this may be obvious from what you
Yeah.
said already, but are these initial functors going to be initial objects in the functor category?
No, and the terminology does not come from that. It comes from this little example, which is that one way to get an initial functor is to start with an indexing category that has an initial object. But the initial functors are not themselves initial in any category that I know of. What? It's not a good name. It's not a good, and it's even worse in the original literature tended to talk about the dual concept, which are final functors, supposedly the ones that preserve any colimit. And then people started calling what I've called the initial functors like the cofinal functors, which is truly cursed as a bit of terminology. So yeah, I think the terminology is not great, but that's what it is.
Well, the cofinal originally usually meant final.
Oh, that's.
Cofinal subset of a poset is a final functor.
There you have it. So, yeah.
To clarify, by diagrammatic reasoning, you just mean like the reasoning you would usually do by diagram chasing?
Yeah, that's a good question. So one of the things that yeah, I mean, I do think that this reasoning is somehow related to what people would call diagram chasing. Traditionally, the most traditional form of diagram chasing is in some kind of like, typically like an additive or abelian category. So one actually interesting question about this stuff is, you know, I think I know how it all generalizes when you want to introduce finite products, but what if you wanted to work in like some kind of additive category? What things might have to change? I don't know. It's an interesting question, but yeah.
So, and what is diagrammatic reasoning? You just mean like reasoning with diagram. Does that
Yeah, I mean, it's not a formal term. It's just supposed to convey, like as I think this example brought out, this is connected to the way that people reason with diagrams. Often, but one notable thing about this is that this calculus is not the calculus like of pasting diagrams in like a 2 category or something, right? The pasting in that sense is one directional. Like you can paste things to get bigger things, but you can't unpaste them. This is bidirectional, right? So it goes either way, and that's maybe this is a good opportunity if I have a moment to point out a counterexample as to why weak equivalence is not the same thing as commutativity. So weak equivalence does not preserve commutativity necessarily. So let's say, consider this. I think this is probably the minimal counterexample. So consider this picture. This functor, this is a weak equivalence. It's a congruence reduction. Another way to see this is that the limit of these diagrams when they exist is the same. What is that limit, by the way? Right? What is the limit of either of these diagrams? Yeah. In general, it's the equalizer. So in general, the limit is the equalizer of f compose g with f compose h. Now, if we suppose further that like if we could have that like fg is equal to fh, in which case the limit of both diagrams is just x, but we don't have to have that g is equal to h. So that is, yeah. So it's interesting. How is it connected? People usually want to, as far as I understand, when people talk about formalizing, like diagram chasing, it's often in the context of like pasting diagrams in something like as a special case of pasting in a 2 category or something. But I don't think that's what this is exactly. Yeah.
Also, I mean, like, so if you had, like, for instance, like a very strong form of completeness result, this would actually be like some sort of normalization or saturation result, where basically starting from some diagram, you could just like saturate that with all the equations in that, and then you would basically be able to read off from that, like, okay, you know, this sub-diagram of the saturated diagram continues to tell me that the
Saturated diagram is the generated discrete operation.
Yeah, so I didn't get to that part, but there is a optimal choice of weak equivalent diagram to any diagram, and that's a fun story. But we're well way over time. So yeah. Okay.
Let's
Yeah.
thank Kevin again.
Yeah.